Okay, it's my pleasure today to represent Professor Alessio Marrani talk, University of Hertfordshire, Okubo Algebra and New Approach to Quantum Chromodynamics. Please.
Thank you very much. So let me say it's a real pleasure to be here and to give a talk here. So let me share my screen. I would like to talk first of all Ivan Kaigorodov, which has been very pleasant to allow me to give a talk. So let me share my screen and start my talk. Okay, so you should be seeing, you should be seeing my my screen, and then let me start my presentation. Okay. Okay. All right. So you should be seeing my screen. Okay. So this talk will be, I would say, a kind of strange talk in the sense that is at the border between mathematical physics and high energy theory, high energy theoretical physics. I myself am a kind of hybrid of a high energy theoretical physicist and mathematical physicist. I would like to say pardon to all the experts in the audience. I will be talking about various, topics in non-associative algebras. Probably there are people much more experts than me, but I would like to talk about them in the spirit of the application to high energy theoretical physics. Indeed, today I will be talking about possible new ways to look at an important quantum field theory, which is quantum chromodynamics, so the gauge theory of the color fields, which is one of the most important quantum field theories nowadays, in relation to the Okubo algebra. This has never been done so far. Is the very first time, to the best of my knowledge, and essentially this is the summary. Is the summary of the talk, and I will be following quite strictly the paper on which the talk is based. There is a paper which has come out this year. Is a joint paper with actually two mathematicians, Daniele Corradetti from the University of Algarve in Portugal, and Vittorio Zucconi from the University of Udine in Italy. Okay, so let me start by considering three types of eight-dimensional composition algebras, and let me recall some very basic facts. Okay, so apologies for the experts in the audience. I will be really mentioning something very basic at the start. So essentially, I will be starting from an algebra, which is a vector space endowed with a bilinear product. And of course, we all know that there are various types of algebra depending on the specific properties of the product. And of course, commutativity, associativity, alternativity, flexibility. Of course, there are implications in one sense, but not in the other, generally. We, of course, will be interested in composition algebras. So, essentially, all these algebras will be characterized as a tripole, okay? So, essentially, a vector space, a bilinear product, and a norm, which is which is such that the algebra is a composition algebra. In general, this will be, as we all know, these eight-dimensional composition algebras are, of course, non-associative, and in particular, we will be considering the generalized Hurwitz theorem, These numbers that you will see in the text, of course, refer to the references of the paper. So you can actually refer to the original paper, or if you are really curious, we can look at the references. So essentially, the generalized Hurwitz theorem states that only 16 composition algebras exist on the reals, because we will be talking about algebras on the reals, because physics is sensitive to the subtleties of the real numbers with respect to the complex numbers. And 7 of those are, and they are called the Hurwitz algebras, as you know. They include the division algebras, reals, complex numbers, quaternions, and octonions, along with their split companions. So the split complex numbers or hypercomplex numbers, the split quaternions, and the split octonions. Then there are another 7, a set of 7 algebras, which are called para-unital, which through a certain trick can be obtained from the division algebras. These are closely related to the Hurwitz algebras. They are indeed named para-Hurwitz algebras. And finally, there are other two composition algebras, one division and one split. They are both non-unital and 8-dimensional, and these are the real forms of the Okubo algebra. I will indicate with this kind of capital calligraphic O, and then the other one with a subscript S, the split case. But I will essentially talk here about the first one, so the divisional Okubo algebra. And as I said, we will be start and compare 3 8-dimensional division composition algebras in this list, given by the generalized Hurwitz theorem. And these are 3 non-isomorphic, of course, algebras, are the octonions, which are alternative and unital, the para-octonions, which I will denote with a P in front of the math bold capital O. These are non-alternative and para-unital in the sense that they have a para-unit, which I will define later, and the Okubo algebra, okay, which is non-alternative and non-unital. And essentially the properties can be summarized in this simple table, in which I list all the important properties, important for essentially for my purposes in this talk. So you see in particular that they are all composition and all flexible algebras, and only the octonions are alternative, and only the octonions are unital. Okay, in particular, the para-octonions are para-unital and the Okubo algebra is non-unital. So as not units, but only idempotents. And we will also, consider the automorphism groups. They will play a kind of important role. Of course, in the case of octonions and they are para-cousins, the automorphism group is G2, of course, over the reals is the compact real form, which is usually denoted with a -14, which denotes the character of the real form, so it's the totally compact real form, while for the Okubo algebra is SU3. And then already from these, something, a bell should ring in your head, in the sense that SU3 reminds us, is hinting us to the gauge group of the quantum chromodynamics, to the color gauge group. Okay, so this is already a suggestion that the Okubo algebra may find an application there. Okay, let's start with more well-known, with a better-known with a better known algebra of the octonions. Of course, these are specified once again by a triple, and essentially they are defined, they can be defined as an 8-dimensional real vector space over the reals with a certain basis, which is endowed with a bilinear product, whose multiplication table is given below and can be pictorially essentially summarized by a kind of finite geometry, an example of finite geometry which is quite famous, which is the Fano plane. Okay, and this algebra is non-associative, and in general is non-commutative, of course, but is alternative and flexible, because alternativity implies flexibility. And about the norm, of course, one must before introduce a certain involution, which allows to define the conjugation. So the definition of a conjugate octonion, and the norm then can be defined is the Euclidean one. And of course, the norm is such that the octonions are a composition algebra, and the norm can be defined, of course, like as the product of an element with its conjugate, which in general holds for every Hurwitz algebra. Of course, this is a division algebra, and the polarization of the norm allows to define an inner product, and I mean, these are features that we all know. Of course, the rigorous definition of the conjugation involution is essentially the makes use of the orthogonal projection on the unit element 1. And an important property is that the canonical involution in the octonions is an anti-homomorphism with respect to the product. That is to say that the conjugate of x dot y is equal to y conjugate dot x conjugate. Okay, is inverting the order of the product. Okay, then the second 8-dimensional composition algebra we will be considering, which is somewhat an intermediate algebra between the octonions and the Okubo algebra, is the para-octonionic algebra. You see, in this case, we start from the same vector space, but we define a different bilinear product, which can be defined in terms of the octonionic product and the conjugation involution, as in 1.4. And in this case, one can prove that still we have a composition algebra. Of course, attention should be paid to distinguish between the para-octonions and the split octonions. Because the split octonions are a split algebra, they are not composition, they are not division, sorry. But the para-octonions are essentially division. But the important point is that differently from the octonions, they are not endowed with a unit, but only a para-unit, which means that essentially there exists an element which I denoted with one bold, such that multiplied for any element of the para-octonions, essentially is reverting it into its conjugate. Okay, and so that is the definition. Still, as I said, the para-octonions are a division algebra, and more than this, we can still move to another 8-dimensional algebra. But before that, before that, we can think about this. There is an important fact. The important fact is that the octonions also admit an order 3 involutive automorphism. This is an important point which essentially allows to define the Okubo algebra. And this does not happen, for example, for other lower dimensional composition algebra. Okay? A possible definition of this order 3 involutive automorphism tau essentially is the 1.5 is action on the basis of the vector space, which I previously introduced. And you see that it acts as the identity on E0, E1, E3, and E7, and instead acts in that funny way over the others, over the other basis vectors. And essentially, one can define a modified, another bilinear product over the same vector space as the octonions and para-octonions by exploiting this tau map. Okay, you see that both tau and tau square appears, and essentially this allows to define a new algebra. This is called the so-called Peterson's trick, because essentially the mathematician Peterson was the first one to introduce this, as far as I know. And this is one possible definition of the Okubo algebra. This algebra is a composition algebra. Does not have a unit or para-unit, but has only idempotents. Okay, still is a division algebra because essentially x asterisk y, where the asterisk denotes the Okubonic bilinear product, essentially from the definition is equal to tau x conjugate octonionic product with tau square y conjugate. If this is 0, then either tau x conjugate or tau square y conjugate are 0, of course. And recalling that tau is an automorphism, this implies that either x or y are 0. So essentially, this is a division algebra, and this is one possible definition. But especially for physicists, there is another way to approach the Okubo algebra, and essentially is by noticing the following, that I can consider the set of 3 by 3 Hermitian traceless matrices over the complex numbers. Okay, and this essentially is a Jordan algebra, or better, more precisely, is the traceless part of a simple Jordan algebra, I should say, because it's German, Jordan algebra. And of course, it's not closed under the Jordan product, which is essentially 1/2 the anticommutator of the matrix realization of the algebra, because of course this is traceful. But instead, one can modify the product a la Michel-Radicati, in the sense that one can essentially subtract the trace part of the product. And of course, this will be traceless. So, I mean, with the Michel-Radicati product, the traceless matrix algebra is closed with respect to this. And Okubo was the one that found a funny this funny algebra by further modifying the Michel-Radicati product, which is given by 1.7, where essentially mu is a certain complex number, where essentially you see that is given here. And you see that the mu as real part is nothing but 1/2. So essentially, the real part of the asterisk product is nothing but the Jordan product with the Michel-Radicati correction minus 1/3 trace of x y, where of course the juxtaposition is nothing but the standard matrix product. But then there is also a imaginary part, okay? Then there is this imaginary part, and one can see that the asterisk product is bilinear, is non-symmetric, because you see that there is in the second term on the right-hand side of 1.7, there is a mu conjugate. And the antisymmetric part is indeed proportional to the imaginary part of mu, which is the square root of 3/6. As I said, this is a deformation of the Jordan product, or better, of the Michel-Radicati product. Okay. And one can prove, and it's not immediately evident, one can prove that essentially this algebra that was found by Okubo in the late 70s is absolutely is isomorphic actually to the algebra that was introduced, as we saw, by Peterson, with the trick based on the rank 3 automorphism too. Okay. And but there is an important thing, that this approach to Okubonions, to the Okubo algebra, allows us to stress the fact that essentially the Okubo algebra is nothing but the traceless part of the algebra, of the simple cubic Jordan algebra over the complex numbers, which indeed is present in the classification introduced long time ago by Jordan, Wigner, and von Neumann of the Jordan algebras. Its traceless part endowed with a peculiar deformation of the Michel-Radicati product. And there is another peculiar property which is not shared by any other algebra which I know of, which is the fact that the algebra, the Okubo algebra, coincides with the algebra of generators of its automorphism group. Indeed, essentially the basis elements of the Okubo algebra, which allows to parameterize the Okubo algebra, can be taken to be the generators of the Lie algebra SU3, which is the algebra of derivation of the Okubo algebra itself. So the fact that in general the algebra coincides with the essentially with the adjoint representation of its automorphism group is unique, as far as I know, to the Okubo algebra, and we will be coming back to this point later. Okay. So, for example, there is no, of course, unit. There is, for example, an idempotent element, like, for example, the one given in 1.8. Okay. And essentially, as I said, the other, this can be taken like the first component in a basis for the Okubo algebra, and the other elements can be taken to be the one given by 1.9, and these are nothing but proportional to the usual expression of the so-called Gell-Mann lambda matrices. What are the Gell-Mann lambda matrices? The Gell-Mann lambda matrices are Hermitian traceless matrices which define a basis for the Lie algebra SU3 in its fundamental three-dimensional representation. Okay. So the message is that 1.8 with 1.9 define the 8-dimensional vector space on which one can introduce the Okubo algebra. Okay. And okay, so in this realization of the Okubo algebra, the norm is nothing but proportional to the trace of the square of an element, where essentially the square is defined, since this is a matrix algebra, is defined simply by x times x, where the juxtaposition is nothing but a matrix product. And then it is easy to show that essentially this norm n has a Euclidean signature, and so it's associative and has this all the properties is composition. Okay, and of course there is as we saw, we are essentially highlighting the fact that these three composition division algebras, let me repeat again, the Octonions, para-Octonions, and the Okubo algebra, they share essentially the same vector space, but it's important they have completely different bilinear products. So concerning this, there should be an easy way to map one into the other. And indeed, this table is summarizing. This table is from the introductory part of my paper. And you see that this allows essentially to map from one algebra to the other, okay? Where the small dot is the octonionic product, the big dot, the fat dot, is the para-octonionic, and the asterisk is the okubonic product. Okay, so now we define the playground, and let's look at the symmetries of these algebras, because for physics, for high energy theoretical physics, of course, we have to look at the symmetries. And of course, there is the first and the simplest of the symmetries is the special orthogonal group associated to an algebra A. In particular, the identity connected component of this group. So it's the group of the endomorphisms of A that preserve the norm, which defines the algebra as a triple. Okay. Then, of course, there is the automorphism group A, which is the group of the linear identity connected isomorphism that preserves the algebraic structure. Okay. And let me say that in general, of course, Auth A is an element of SOA, but the converse is not necessarily true. So in general, the automorphism group is a proper subgroup of the special orthogonal group over the algebra. And then there is triality. Of course, the eight-dimensional vector space should ring a bell, because should be hinting to something related to triality, of course, to the triality of the fundamental representation of D4. In general, the triality characterizing an algebra is defined as the group of triples of orthogonal transformations which respect its algebraic structure. So it's defined essentially as in 1.21. Okay. And in general, there is this relation between these symmetries. Okay. And of course, the automorphisms are in general inside SOA. Okay. And this is the table which summarizes these symmetries for the three composition division algebras, eight-dimensional ones, which I've been considering. Okay, so you see essentially that the automorphism group is G2, is the compact real form of G2 for the octonions and the para-octonions, and is SU3. And we will see what is the relation between G2 and SU3, which is not maybe the one that one might expect. And you see that for SOA and 3A, in this case, they essentially are isomorphic and are given by the spin covering of D4, spin 8. Okay, the spin group in 8 dimensions. Okay, now I will start a very flashy digression about about physics. Okay, so far I've been talking about mathematics, but then it's time to introduce some physical elements. I will be very fast, but essentially this is something that is a kind of textbook material about QCD. So QCD has a long history and an interesting one, actually, I would say, which dates back to Gell-Mann and Zweig, and essentially is the quantum field theory which describe the strong force. The strong force, which is essentially responsible for the interaction of quarks inside the nucleons, for example, and is essentially given by a Young-Mills part, which is related to the mediators, to the bosons, to the gauge bosons of the color SU3 gauge groups, so to the gluons. And then there is the matter part, which is given by a Dirac-Lagrangian for the quarks. Okay, and then there is also another pair of Lagrangian densities, which I will not be talking about, which are kind of related to the gauge fixing to the ghosts. But what is important is that the gauge group is non-abelian, is SU3. So essentially, the field strength associated to the gluonic fields essentially contains these gluon self-interactions, which makes essentially in the gauge sector all the difference with respect to quantum electrodynamics, no? Which is based instead of U1 on an abelian gauge group. So these are the self-interactions of the gluons, which are telling us that the free theory essentially is already an interacting theory, if we just look at the Young-Mills sector. And of course, also the derivative inside the Dirac part for the matter fields, for the quarks, is covariantized with essentially these T small are the generators of the gauge group, because essentially the small Latin indices are essentially in the fundamental representation, run from 1 to 3 of SU3, while the Latin capital indices are in the adjoint representation. In the 8-dimensional adjoint representation. So this is the Lagrangian density, but QCD is important. Why? Well, because essentially there are aesthetic reasons. For example, as there is the beauty of the mathematical structure of the scattering amplitudes, for example, in the supersymmetrized QCD, but also because essentially there is a millennium problem. So there is essentially $1 million for proving that Young-Mills theory is confined, because the QCD belongs to the class of non-abelian Young-Mills theories, and they exhibit a very strange phenomena. The very strange phenomena are essentially two. Of course, I will not be entering in detail in this slide, but for example, you can notice that there are these self-interactions of the gluonic fields, which are a direct consequence of the fact that the gauge group is non-abelian. Indeed, for example, in the amplitudes, you see that all is proportional to the structure constants of SU3, for example. And the first phenomena is the fact that this theory is asymptotically free. What does this mean? This means that essentially the coupling constant decreases at high energies. Okay. So this means that that there is a radical difference with respect to, for example, quantum electrodynamics, which is a quantum field theory based on an abelian gauge group, essentially U1. And and essentially, sorry, then there is another, yeah, there is this one. The fact is that there is asymptotic freedom, so whenever you increase the energy, the theory is becoming asymptotically free. This is exactly the opposite to what appears for QED. And this also does not allow essentially to perform perturbative approaches to QCD. On the other hand, there is also the so-called confinement, which is exactly the opposite. So the confinement is telling you that you will never see, for example, quarks free quarks, because essentially when you separate them, they hadronize, and you will always see something which has integer or vanishing electric charge. So this is a kind of censorship for the fractional electric charges of quarks. And these two phenomena are hinting for something radically different from the the mathematical entities which allows for an algebraic approach to quantum electrodynamics. Okay. And the basic idea of the employment of the Okubo algebra in quantum chromodynamics is the fact that the absence of a unit should be related to the fact that one cannot really perform a perturbation theory in QCD. And also the confinement should be related to the non-unital character of the Okubo algebra. But the first evidence, of course, is related to the fact that the automorphism group of the Okubo algebra is SU3, and this might be taken to be the gauge group of coinciding with the gauge group of quantum chromodynamics. Okay. Here I would like to stress and start once again from the octonions. So the role of the octonions in algebraic model of particle physics, it's now kind of well known, and we will see that it's completely different from the possible algebraization of QCD due to the Okubo algebra. At the moment, there is no way to reconcile this. So in some sense is one or the other, and I will try to highlight the reasons for this statement. So let me start with the octonions once again. Of course, in this case, we saw that the automorphism automorphism group, whose the algebra is the algebras. And in the case of the octonions, I just said that the derivations are nothing but G2 is the Lie algebra G2 minus 14. And it's important to say that the octonions sit in the 1 plus 7 of G2. So in a singlet, which is nothing but a unit, and in the fundamental 7-dimensional representation of G2. And these are nothing but the imaginary octonions. Okay? Let me say that this is the first evidence for the unital, this essentially the presence of a singlet in the algebra seen as a module of its automorphism group is the direct evidence of the unitality of the algebra itself, because the same does not happen for the Okubo algebra. Now, the relation between essentially spin 8, the triality spin 8, and G2 is simple, given by the usual fact that G2 can be embedded into spin 7 and spin 7 inside spin 8, okay? In the way that I am reporting here for the three triality related 8-dimensional modules of spin 8 and then for the adjoint of spin 8, okay? Yeah, so as I said, essentially the unitality of the octonions essentially is given, is related to the presence of a singlet of the automorphism group in the algebra itself, seen as a module over the automorphism group. And so there is an important point that the SU3, where is the SU3O? Here I denote this SU3 with a subscript O, where O, is denoting the octonions. Well, the SU3, which might be used for the octonionic algebraization of the strong force of the QCD, is a maximal non-symmetric SU3 inside the G2. So it's the one for which the 7-dimensional representation is of G2 breaks into 3 plus 3 bar plus 1. And essentially amounts to fixing one of the 7 imaginary octonionic units. So one fixes one of the 7 octonionic imaginary units, and this breaks the automorphism group G2 into SU3O into the octonionic SU3. In passing, I noticed that this is related to a certain model for the 6-dimensional sphere, in which the complex structure is manifest. So, for example, there is another way of presenting G2 minus 14, which is given by this octonionic SU3 in semi-direct product with a 6-dimensional sphere, denoted essentially as this coset space. Okay, but this is just in passing a nice fact. And of course, there are 7 ways to define this maximal non-symmetric subgroup of G2, this octonionic SU3, because there are 7 octonionic imaginary units, of course. And by doing this, essentially, the octonions break down, you see, 1 plus 7, which is essentially the conceivement of the octonions as a module over the automorphism group, breaks down into C plus C3, which at the level of representation is 1 plus 1 plus 3 plus 3 bar. Of course, here, I'm sorry, I'm using the physicist way to denote irreducible representation of the algebras with the dimensions in bold, no? And so this is somewhat customary in theoretical physics. Okay, so this is the story about the octonionic SU3. And of course, the application to QCD, as I said, stems from the fact that I am assuming that the gauge group SU3 color is SU3 octonionic, which I just defined. And essentially, when I break down the octonions into representations of SU3 octonionic, of course, I got a pair of singlets and a 3 plus a 3 bar. And of course, the 3 can be related to quarks under, the identification 2.12, and the 3 bar can be related to the anti-quarks. So essentially, there is this result given by 2.14, where I take a pair of triplets of octonions, and this is enough to cover all, to contain all quarks and anti-quarks of the standard model. Namely, there is a 3 plus 3 bar for every quark flavor, because the quarks come in flavor. So up, down, charm, strange, top and bottom of the standard model. And then there is a total of 12 color singlets, which can be identified and which are available. okay? So essentially by a pair of triplets related, each triplet is related by triality of the 8-dimensional representation of spin 8, and one can cover all the quarks of the standard model. And of course, one can also draw this picture, which essentially is a picture dating back to the early times of QCD. So the quark model by Gell-Mann, for example, Gell-Mann and Zweig. So essentially, the three colors of a quark are in the reducible representation 3 of SU3 color. Then there is, of course, the three anticolors for the antiquark Q bar. And then there are the 8 gluons in the adjoint representation 8 of the SU3 color. Okay? This is somewhat understood. So there are algebraic models of the QCD based on the octonions, at least for the quarks. But what about the gluons? The gluons, I just said in passing, if you noticed, that are essentially the gluons are in the adjoint. But that we didn't see any adjoint of SU3 around, at least from the octonions, stemming from the octonions. No, we just looked from 213. We just found a triplet and an anti-triplet and 2 singlets. That's why one could resort to the Okubo algebra. Because essentially, in the case of the Okubo algebra, we have that the automorphism group is an SU3, which we will denote with the subscript Okubonic, the capital calligraphic O. And we will see that this is a completely different SU3. In particular, that share no rank 1 subgroup with the octonionic SU3. We will see this. But an important point, which is the expression of the fact that this is a non-unital algebra, is that there is no singlet in the Okubo algebra as a module over its automorphism group. This is consistent with the fact that I just said that the Okubo algebra is coinciding with the adjoint representation of its automorphism group, so with the 8-dimensional one. So 3.4 is telling us that the Okubo algebra is nothing but the adjoint representation of the Okubonic SU3. You see that there is no singlet, there is no unit. The idempotent that we have been talking about is essentially one of the 8 generators of SU3 Okubonic. Is mixed there. Okay, any idempotent of the Okubo algebra. So, how is this SU3 related to spin 8? Remember that in the case of, let me before compare with the octonionic case. In the octonionic case, remember that the SU3 octonionic was maximal inside the G2, which in turn was related to spin 8 through this chain, which is well understood, no? So if you want to descend from spin 8, essentially is spin 8 going to spin 7, going to G2, going to SU3, with a chain of maximal embeddings. Okay? Instead, the Okubonic SU3, so the automorphism group of the Okubo algebra, is, let me go to the relevant slide, is maximal, is a maximal subgroup with no commutant inside spin 8, inside the same spin 8. So this is a consequence, is a trivial consequence of the fact that SU3, of course, has a Cartan-Killing form, which is invariant. And so essentially can be, so as a rank 2 symmetric invariant tensor, and so can be embedded into of course, SO8, but of course, since due to triality, essentially what is relevant here is the spin covering, so it's spin 8. So SU3 is maximal non-symmetric subgroup inside the spin 8. Okay? And this is a consequence, if you want, of a famous theorem by Dynkin. This is crucial because you will see that this is a completely different SU3 subgroup with respect to the octonionic SU3. Indeed, the general message is that SU3 Okubonic is completely different from SU3 octonionic. In particular, SU3 Okubonic is not a subgroup of spin 7 for the very reason that is maximal subgroup inside spin 8. Okay? The lack of a unit implies that the octonions are irreducible under the action of the automorphism group. There is no singlet. They sit in the whole adjoint representation. And the general idea is that the lack of unity, as I said, might be related to the intrinsic non-perturbative nature of the foundational phenomena of QCD, of the strong force. Okay? And that's it. So essentially, there is another algebraic approach to the algebraic characterization CD, in which SU3 color is no more SU3 octonionic, but instead is SU3 okubonic. And this allows to immediately provide a model for the, not for the quarks, but for the gluons, so for the gauge sector. The gauge sector of the gluons, so the gluons will be nothing but related to the basis elements of the Okubo algebra, given by 3.7, no? Because the gluons are the gauge fields of the color SU3. If we assume 3.6, then essentially the generators of SU3 okubonic may be identified with the different gluons. This is a completely democratic modeling of the gluons, because all the gluons are massless and stand on the same footing color-wise. And this is a consequence also of the fact, which I noticed before, that essentially a possible realization of the Okubo algebra is in terms of the Gell-Mann matrices, which are in one-to-one correspondence with the generators of SU3 and with the 8 gluons. Okay. Of course, you see, we are always talking about symmetries and representations. I never tried so far, or in this talk, to really write down some invariant Lagrangians, starting from this kind of algebraic approach. Even though this is possible, of course. And let me see that this Lagrangian, of course, should be invariant under the automorphism group of the underlying algebra that we choose, either the octonions or the Okubo algebra. And the forms, I mean, the functional structures appearing in this Lagrangian density, in this will be Lagrangian density for QCD, will be radically different. Because, of course, the kinetic terms will be related essentially to the quadratic Casimirs of the automorphism group, in one case G2, in the other SU3. But then let me remind you that think of invariance for G2 is generated by the Cartan-Killing form, the quadratic polynomial, but then also by a degree 6 Casimir, polynomial Casimir. In the case of SU3, the ring of invariance is still finitely generated, is two-dimensional, and is generated besides the Cartan killing by a cubic polynomial. So the structures are radically different, and it's easier, of course, to make sense of the cubic Casimir in the Lagrangian instead of a sextic Casimir in the case of G2. So there are, of course, works in progress in this direction, but let me say that the case of the Okubo algebra as a source for an algebraic modeling of the QCD is much more promising than the octonionic one. So this is something that is still going on and is very interesting. Yes, so I would like to finish essentially by summarizing and trying to understand what's happening here. So essentially, I presented the two different sources of an algebraic approach to modeling the strong interaction. On one side, we have the octonions, and on the other side, we have the Okubo algebra. They are both composition, division, and algebras, but there is an important difference. One of the differences is the lack of unit for the Okubo algebra, which seems really more consistent with the non-perturbative nature, intrinsic non-abelianity of the gluonic interactions in QCD. An important difference is that while the octonions seems more, more consistent with a modeling of the quarks of the matter sector, for the very reasons that the octonions as a module over G2 over their automorphism group are in the 1+7, which breaks further as 1 plus 1 plus 3 plus 3 bar under the maximal embedding of SU3 octonionic in G2. And then the 3 is nothing but the color triplet of a quark field. On the other hand, the Okubo algebra instead sits in the adjoint representation of its automorphism, the Okubonic SU3, and essentially this does not break. It's the adjoint. There is no singlet. It's an irreducible representation. And of course, this, if one identifies the Okubonic SU3 with the SU3 color gauge group of QCD, this offers a model for the gluons, so for the gauge sector of QCD. So in a sense, as I've written here, these are essentially two complementary physical interpretations I would say two complementary algebraic interpretation of QCD. And as I say in the footnote, essentially this physical complementarity amounts to switching between one bilinear product to the other, because the vector space is the same, but the important difference is the bilinear product, the octonionic one on one side and the okubonic one on the other. Finally, just a note, these two SU3s do not coincide, they are not isomorphic, they are totally different. So this is, as I said, probably, it's telling us it's either, it cannot be both of them. They cannot be identified. Of course, they are completely different subgroups of spinate. One, the Okubonic one is maximal, non-symmetric into spinate. The other one instead is maximal inside the G2, which is next to maximal inside spinate, as I showed. And can be showed, this is in the paper, they don't even share a common rank 2 subgroup. So the message is that SU3 Okubonic is completely different from SU3 octonionic. They don't even share a common SU2 subgroup. Okay, So in some sense, they are not, one should choose one or the other, cannot be choosing them at the same time. And of course, this is problematic. Because of course one would like to provide an algebraic modeling of the gauge and matter content of QCD. We are studying different ways out to this. And it seems essentially that if one starts from, essentially from a theory which has a larger symmetry, like for example related to spin 16, which is maximal inside the 8. So this relates essentially to the whole dream of starting from a theory, a quantum field theory is based on E8, which is the largest exceptional group. And we know that E8 contains maximally spin 16. And essentially spin 16 can break in spin 8 times spin 8, where essentially one spin 8 becomes responsible for the gauge sector, because it will contain spin 7, G2, and then the SU3 octonionic. On the other end, the other spin 8, which is commuting with the previous one, contain maximally SU3 okubonic. In this way, one can make sense, of course, with of the gauge sector and the matter sector of QCD at the price of having other fields, which one should find a way to freeze them or to cover, I mean, to hide them in some way. I will say that this is essentially all I wanted to say. This figure is essentially the message that SU3 octonionic is different from SU3 okubonic. And yeah, there are some other subtleties which you can read from the paper. So if you are curious, you can, if you have any question from the paper, you can of course reach out to me. And to summarize, essentially, this is the first attempt to introduce an interpretation for the real Okubo algebra, in particular in relation to QCD. The comparison with octonions essentially produces two kind of complementary pictures, two kind of complementary subgroups, SU3 subgroups of spin 8, which is essentially the orthonormal, the orthogonal group consistent with both the octonionic norm and the okubonic norm. But the fact that the Okubo algebra is lacking unity seems to be consistent with the non-perturbative nature, intrinsic non-perturbative nature of QCD phenomena, such as asymptotic freedom and color confinement. And of course, this is still a work in progress. This is the first paper of this kind. We are still working, and there is a long way, I guess, but it's kind of promising, and at least, I mean, there are various hints, tantalizing hints, I would say, to a possible field theory realization of this. Of course, the road is still long, but there are essentially the analog papers for the octonions. So one essentially could try to repeat mutatis mutandis, of course, the same approach that is known for the octonions for the Okubo algebra. I think that I'm done. I would like to conclude with a sentence from Okubo. You know, this is essentially Okubo was a theoretical physicist which made the transition at the end of his career towards mathematical physics. In his book on the relevance of octonion and other non-associative algebras in physics, he said that it's still possible that non-associative algebras may play some essential future role in an ultimate theory. Essentially, he didn't have time to really dig deep in physical interpretation of the Okubo algebra, which I mean he essentially found in his approach. And in the present paper, we have suggested a fierce, possibly even stranger opponent than Octonions, the Okubonions. So I would like to thank you for your attention.
Thank you very much. Let us thank the speaker, please.
Thank you.
Do we have questions related?
Thank you, Florin. I'm glad that you appreciated. There is a message on the chat.
Okay, so if we don't have questions,
Yeah,
let
I would
us
have
speak.
a question.
Let us
I
thank
just
the
don't know
speaker
how
again.
I don't know how Zoom works, so sorry. Yeah, so thanks for the excellent talk. I try to learn a bit of physics. I'm not good at the end of the physics bit, but my question would be, what about color algebras? And why? I mean, I see the advantage of Okubo algebras very clearly, and color algebras for me would be another way forward. And of course, this is something which has been done, and Alberto will know much more about this than I do. But I would ask you, what's your approach? What has your approach? What is not given by the approach using color algebras, which are also non-unitary, which also have similar features like you just presented?
Thank you, Susan. I have to say that color algebras. I always have been curious. I'm not expert about those. I will be very curious to learn about them, and I think that they might provide. The fact is that I came to know about Okubo algebra because I studied octonions. I mean, in the physical application of octonions, in particular in high energy theory, in high energy theoretical physics, and then I came to know Okubo algebras. Probably you were alluding to and the color algebras. You were mentioning that someone is expert.
Alberto
I
Duque, yes.
Yeah, I know that El Duque, has been writing a lot on the color algebras. I never had time, and I am a physicist at the end of the day. So, I have some. It's not completely immediate for me to read these papers and grasp the
I
real.
totally understand because I struggle reading the physics papers. I came across something which Penrose 2 years ago. I started
Yeah,
trying to learn physics because Penrose noticed that there is a connection with the split between the split octonion algebra and his twistors, the famous twistors by Penrose.
absolutely,
And
absolutely,
I am pretty
and
sure, but I need to find someone who is fluent in physics, and I'm not, because I think there is a direct correlation between color algebras and twistors.
this is an interesting project. Absolutely, we can try to dig
And
deep.
so I was
The
thinking, if you're
point.
interested, I sent you an email.
Yeah, yeah. I read it and I didn't have time to answer, but I will do it soon. The point is, as I said, this is a talk and this is a team. It's a research at the border
Hmm.
between mathematics and physics, essentially
Yeah.
mathematical
And I
physics
think it's a very good
and
one,
the
to be honest. I think it's the right way forward.
and the point is that it's hard to find people that you have to make a mathematician and a physicist sit down and collaborate, which
Yes, I
to my
volunteer, I
experience is
volunteer.
very hard. To my
Alberto too,
experience
I
is
can
very
see. Alberto has a question too, so I leave you to it.
yeah.
Thank you very much.
Oh, you're welcome. Then
Yes,
of course I
please.
will answer to your mail. Yeah.
Okay.
Hi, Susan, and hi, Alessio. Thank you very
Hi,
much for the
Alberto.
talk. Just
Hi.
about this color algebras that Susan mentioned, there you have unital algebras. The automorphisms are SU3, and the composition of the algebra as a module for SU3 consists of 1 plus 3 plus 3 bar in your notation. So it's not that far from what happens for the octonions.
For the Octonions.
The only thing is in the octonions, you have 1 plus 1 plus 3 bar. Here you have just 1 plus 3 bar. So you have the unity and SU3 acting there again.
Okay.
So
So essentially, this is less appealing in some sense, because essentially I would like to have something which is an algebraic structure without the unit, such that the very appealing feature of the Okubo algebra for application to QCD, which I think is unique, and please correct me if I'm wrong, is the fact that this algebra sits in what physicists call the adjoint representation of its automorphism group. So coincides in a sense with the generator of its derivations. And as far as I understand, this is the unique case.
Mm-hmm.
And this is very, very nice because essentially, in some sense, the automorphism is such that the Okubo algebra is acting on itself. And this is very appealing for physics. So there is no external module on which an algebra is acting, but essentially here is essentially the algebra is acting on itself. And yeah, that's the point. So, but I have to study color algebras. I mean, I'm not. I only know, Alberto, that there are this very interesting paper by you and your collaborators, but I have to study. I am a poor physicist, and it takes me a while to study, but I'm really interested in this. I mean, thanks very much for your
Thank
comment.
you for the nice talk.
Thanks.
Do we have any other questions, please?
There is hands raised. Yeah. Hi.
Yes, I have a question. Thank you very much for your talk. I thought about this when you were discussing with Alberto about the non-unitality. So the Okubo algebra has, so it's irreducible. And then it has three siblings, so to speak, that decompose into a 3-dimensional and a 5-dimensional submodule over their derivation algebras. It's, I mean, from the octonions, you have the para-octonions by taking conjugation on both, and you can take conjugation on one and on the other. And this is a similar story from the Okubo algebra. Do these appear somehow? They're very curious, these 3 plus 5, and not flexible or anything.
Yeah. This I didn't get all you said because but it's something interesting. You are saying that there is some kind of subalgebra of the Okubo in some sense, such that the SU3 breaks the 8 of SU3 breaks in 3 plus 5, which I guess are module for SU2.
No, yeah,
right?
exactly. So it's not SU. It's a deformation of the Okubo algebra, 3 deformations. And I believe the derivation algebra is SU2, and then
so this
it
is
breaks
yes,
as 3 plus 5.
Yes, indeed, because this is what physicists call the principal SU2, the principal constant principal SU2 inside SU3. No, because SU3 contains maximally SO3, which is isomorphic to SU2. And this SU2 is essentially the constant principal SU2. And let me say that this is the unique case in which the principal embedding is symmetric. Otherwise, usually is non-symmetric. And, this rang a bell in my head because essentially the 8 breaks in 3 plus 5. So I guess you are talking about that. And this might be interesting. Yeah, this is definitely interesting because, of course, SU2, it's always interesting for physics. So I would be interested in seeing this deformation. I'm not aware of this at the moment. And this is interesting. Definitely. I guess I wonder how but these 3 deformations, I guess, at the end of the day, they produce some isomorphic automorphism as SU2. I mean, it's always the same SU2, right?
I think so, yes. It was a long time ago.
I mean, at least at least these SU2s should be mapped one onto the other under inner automorphisms of SU3, maybe something like that. Because I mean, there is at the end of the day, there is a unique principal SU2, so there is a unique maximal SU2 with no commutants inside SU3. So I mean, at the end of the day, but this is very interesting. It's very interesting because, to my knowledge, this is the unique case in which the principal embedding of an A1 subalgebra into a Lie algebra, simple Lie algebra, is symmetric. So thanks for this. Maybe you know, Seidon, I know you very, very, very indirectly, because you have been cited, you have been thanked in a paper which I happened to read by someone, I don't remember the name, some guy from you know, which has Chinese origin, probably.
Yes.
Yeah, probably at your university. You are based in Uppsala, right?
Yes.
Yeah. And
that's cool. I'm glad you know that.
That's cool, because
I can send you the references
because you are thanked as the local octonionic expert in this, in the acknowledgement of this paper. And so, I mean, that's why I know you. And then I have been, of course, perusing some of your papers, but I mean, most of them, of course, are out of my reach because I have other background. But you know, thanks for this, and maybe I can bother you and ask you the precise references of these deformations.
Yes.
Okay, thanks very much for the question. Thanks.
Thank you very much. Thank you.
Thank you very much. Also, so questions? Okay, let us thank the speaker again.
Thank you very much. It has been a pleasure to give a talk, and I don't know if Ivan is attending, but I would like to thank him because you know, I had to attend the conference which is now starting to take place in Dijon, but I couldn't, and then he offered me this chance to anyhow to deliver this talk. So thanks very much.
Okay, thank you very much.
Thank you.
Yes.
Thank you, Ivan. I didn't
the
see
end
you.
Of the evening section.
Okay. Thanks, everybody.
Yes. Okay, bye.
Thank you. Thank you.